Now, so we are going to solve question number A, 4A, I mean A4, this one, of which we are told to find, first of all, we've been given the two half reactions, so we are going to find the balanced equation of the overall cell reaction. Thereafter, we'll proceed and calculate the E cell, and we need to present the cell notation of the same reaction. So the only data that we need to gather on this question is the E cells, or rather the cell potential for each half reaction here. So if you take note, we don't have that in the data sheet here. So first thing first, the E cell for the first reaction is positive 1.20 V, which is voltage. And then for the second reaction, the E is equal to negative 0.14 V. So that's the only data that we need in order for us to proceed and attempt these questions. Is that okay? Hello?
Yes.
Perfect. All right, so let me share the different board so that we can proceed and solve these questions. So the two half reactions that we have, the first reaction is PT 2 plus 2 electrons, giving us PT. So the first one, it is in aqueous state, and the second one, it is in solid state. So we say that its cell potential is positive 1.20 V. Then the second reaction is tin 2 plus aqueous plus 2 electrons. After this, you get SN, which is a solid state. And its E cell is basically negative 0.14 V. So now, the first part, to find the overall reaction, or to write the balance equation of the overall reaction, the first thing first we need to do here, first of all, we need to, from the two half reactions, if you have observed very well that these two half reactions given, they are both reduction reaction. Why are we saying they are both reduction reaction? Because sometimes you can tell from the side at which the electrons are being added. So if electrons are added on the left-hand side of the reaction, or rather on the reactant side, just know that that reaction is the reduction reaction. But if electrons are added on the right-hand side or product side of the reaction, then that reaction becomes the oxidation reaction. So as we can see here, these electrons are added on one side, indicating that these two reactions are both reduction reaction. In a case where you have such a tie, you need to reverse one reaction so that it becomes, if it was the reduction reaction, it becomes oxidation reaction. If it was oxidation reaction, it becomes reduction reaction. Now the question is, which reaction are we supposed to reverse? So you can only reverse the reaction which is having low or rather lower is potential there. So you check from the potential you have, which one is the smallest? If you observe the first one, it is positive 1.2, and the other one is negative. So which one is the smallest? So you reverse the one with the smallest cell potential. So in this case, what you have as the smallest is this reaction. So what do you mean when you say reversing? What you mean is that we are going to swap. The product becomes reactants and the reactants becomes the products. So we'll say reversing equation 2. You have Sn, a solid, giving you Sn2 aqueous plus 2 electrons. Then we are going to have the E cell of this. So it is okay even if the E cell remains, or the sign of the cell potential remains unchanged. Is that okay?
Yes.
All right, perfect. Now that we have reversed, so in this case, after reversing, you are just going to be dealing with the equation 1 and the reversed reaction. So, which means if we want, we can even bring equation 1 here so that we have them close. So we have PT 2 plus aqueous plus 2 electrons. You get PT solid, and its E is positive 1.20 V. Now, to write the balance equation now, you have to go back to the way we balance redox reaction. So if electrons, let's say we didn't have equal number of electrons added and on both sides. In this case, if you look at this, we have in the oxidation reaction, the first one, we have 2 electrons, and in the second one, we have 2 electrons there, which means electrons are what? Balanced. What does that mean? You can cancel them out and add the 2 half reactions. What do we mean adding the 2 half reactions? Which means the reactants will be added on one side and the product will also be added on one side. Therefore, the overall balanced reaction will be, we pick this, so it will be Sn plus, and another reactant we have is PT there, PT 2 plus aqueous, giving you go to the products, Sn 2 like that aqueous plus PT, which is solid. And see, so this one is balanced. And why are we saying it's balanced? We need to check. So first of all, how many PT do we have? On the product side, we have 1. On the reactant side, we also have 1. On the 14, you have 1 as well. The charges, the overall charge on the reactant side is on the first one, tin doesn't have the charge, and the charge here is positive 2. So which means the overall charge on the reactant side is positive 2. Also, for the products, the overall charge is positive 2. Hence, the reaction is balanced. Is that okay?
Yes.
Now, imagine, for example, if we had, let's say here we only had 1 electron added, and here we have 2 electrons added. How would you have balanced it? Do you have an idea how?
I think you swap the charges.
We swap.
Multiply 2. Yes, 2 with the second equation. Multiply 1 with the first one.
Perfect.
That the electrons are able to cancel.
So exactly. So if we had such a case, just like they have said, these two electrons would have multiplied this reaction, and the one here would have multiplied that reaction. Then after that, that's when you cancel the electrons and add the two half reaction. But that's not like the case for this reaction. Everything was well given like that. Right. We can now calculate the E cell. So we know very well that E cell at standard reduction potential, so we say E cell is equal to the standard reduction potential for the cathode reaction minus the standard reduction potential for the anode reaction. So here is the twist. Okay, there's no twist here. Between the two, which one is the cathode and which one is the anode?
PT is the cathode.
Exactly. So PT is the cathode. So that voltage will subtract the anode, which is this voltage. Right. So when you do that, what are you getting?
$1.34 volts.
1.344, right? 1.3?
1.34.
1.34 V. So remember, the sign is positive. So it means this is the E cell for that reaction. Is that okay?
Yeah.
All right. Now, here is the thing. Some tutors or lecturers will say, when you reverse this reaction, like the way we reversed this reaction here, the sign of this also changes, right? That's what I say. But if, let's say, we change the sign from it being negative, let's say we changed it to positive here. So for E cathode, E anode was going to be positive 0.14. That is if we change the sign when we reverse this reaction. So if you are working with this standard reduction potential, which is the reversed one, when you come to this formula for E cell here, okay, where there is negative here, when you want to work with this reversed one, where there is negative here, you add instead of subtracting. So what would have happened is that you are going to put positive here instead of subtraction. The formula was going to be E cathode plus E anode. And then you pick this, which is the reversed, and that one that is unreversed. But if this sign, if you didn't change the sign of this, the formula remains the same like this. Okay, so some people tell you, no, you can reverse, you can, when you reverse the reaction, you can also change the sign. But that's not the case. Sometimes if that happens, if you reverse the sign of the cell potential, it means when you want to bring it on the this formula for E cell, you need to add instead of subtracting. Is that okay?
Yes.
All right, perfect. Now we can go to the last question, which is the cell notation now. So the cell notation, just a brief background, it is basically the shorthand way, okay, It is the shorthand method of representing galvanic cell. So it's the shorthand method of representing galvanic what? Cells. So how does it exist? So you are going to have the reduction, you are going to have the oxidation reaction. On the left-hand side, then double underline the reduction reaction on the right-hand side. So these double vertical lines represent the salt bridge. So if you look at what we have as the two half reactions, these two, so you are working with these two here. The oxidation reaction is this one on top, and then the other one is the reduction reaction. So when we want to write the cell notation, it's going to be, you say, where's my board? Okay, so you are going to have which one? Okay, this one. Tin solid, you write tin solid one line, then you write the one which is in aqueous 2+, you even indicate its state symbol. And if this one had, let's say, concentration, again, you have to indicate it together with aqueous state inside there and put the brackets. If it had concentration, then double underline, you write immediately, you write the speech in aqueous state for the reduction reaction. In this case, we have PT 2+ aqueous state, then one line, and also give the other one which is in solid state, which is just PT solid. So this line, single vertical line, indicates just the phase. So it is just marking the phase between the solid part and the liquid, the aqueous part. And then double vertical lines there represent the salt bridge. So which means this is our this is our cell notation for that reaction. So the right-hand side is the reduction reaction, the left-hand side is the oxidation reaction. Is that fine?
Yes, it is.
All right, perfect. So that is how you can basically deal with or rather solve such a question. So I will allow you to attempt the one on top. Question number 8. A7. A7 is similar to this. You'll be able to get the what's this? The electron potential for each reduction reaction on that table I gave you. We good?
Okay. Yeah.
No questions, right?
No.
Okay. That's very good.